Greetings, Graham Warren again. This time looking at an AnyLogic simulation model for the Antico Caffe Greco case with you. Um, so we'll introduce AnyLogic elsewhere, the palette, the project pull downs and so forth. The model really sits here in this screen called main. So just want to go there. So let me see if I can walk you through the essential elements of this discrete event simulation model. So customers are arriving here, and they arrive in a Poisson process. I'm going to just click on that with arrival rate. So you can see I have a bunch of parameters here. So you can control what that arrival rate is by just plugging in different numbers. Then there's a mean service time, standard service time, standard deviation of the service time of the valves, standard deviation of the service time of the clovers, how many valves you've got in your Caffe, and how many clovers you have. So here, it's clear you can have a mixture of clovers and valves. So this is where the engine room of the simulation is. These customers arrive in a Poisson process at rate arrival rate. Then there's a timer that we've set up here, and you can see that I've got time measure start and time measure end, and they're connected. What they're basically doing is they're measuring from time of arrival to the time of delivery of coffee, of the caffeinated beverage, that interval. And these are going to be recorded, and statistics will be generated from that. So what happens after the arrival and the timer starts, the customer basically tries to grab a server. We think of these servers as coffee makers. They really come with a barista in each case. So I've got a bunch of valves here and a bunch of clovers, and you control how many of each there are. So what happens is customer comes in, tries to grab see if I can click on that for you, tries to grab okay, there we go. So I maybe need to expand this a tad here. But there are alternative resource sets. At first tries to grab a valve. Alternatively, it tries to grab a clover. And then once it's got that, it comes with a barista, of course. Then we have a delay here in the make coffee space, make a coffee block rather. So let me just wait for that to populate. I'm in a reasonably slow connection here. So you can see what the delay time is. It's a little bit of Java that sits here, and basically what it's asking is, if it's a valve that you're dealing with, then use the mean service time, because the mean service time is the same for the valves and the clovers. Use the mean service time and then the standard deviation of the valve. If it's a valve that's been grabbed by the customer, and if it's not, then use the mean service time again and the standard deviation of the service time for the clovers. So you just making sure that your standard deviation is relevant. All right, so then the coffee's been made, and then you release the server. That means releasing the barista coffee maker combination, whichever it may have been, valve or clover, and then you click the stopwatch again, and then the customer disappears from the simulation. So the rest of the simulation, or the rest of the model here is these are the parameters that we've described. These are the resource pools for valves and clovers, getting some statistics together on the queue length, folks waiting for a server, the utilization on the valve and on the clover. This is the histogram from the timer. And we have to, support this with some data sets. So there's a time and system data set that comes from the stopwatch setup. The clover utilization, of course, just looks at utilization of the clovers, same for the valves, and got some technical stuff here, just recording that information. We also get a histogram for the valve utilization. That's really the purpose of collecting the data here, and the same for the. See, this says jury utilization. This was an old version. Let me just go ahead and change that. It's of course clover. So just change that to clover. Okay, I think we're good. And so what I'm going to do is just run this in the base case for you. So there's a little animation here that just shows folks arriving and waiting for a server, and then the coffee is in process, a little automation so you can see what's happening. But we can run this. So to run it, you probably want to set yourself up, and we'll just look at the base case here. So you go to simulation main to set this up, and then you can see the parameters are available here. So the mean service time, irrespective of machine, is 60 seconds. The arrival rate in the base case, we've got 29 customers arriving to each barista. They're working independently in the base case. The service time the standard deviation of service times is 10 seconds. So I think that's incorrect. Yeah, here it is. For the clovers, it's 10 seconds. And I have one clover, no valves, and it's a little small, I understand. It's hard to rescale it without messing things up here in the video, but this reads 60 for the mean service time, 29 for the arrival rate, 30 for the standard deviation of the service time for valves. Not relevant here, but just put a number in. Number of valves is 0, so that makes it irrelevant. Number of clovers 1, and standard deviation of the service time for clover is 10 seconds. All right, and then we're going to go ahead and run it just to see how this thing looks. Probably want to get rid of the annotation here. We get this pop-up window. Okay, and it's running, and we can control the speed here. You can see the folks coming in, getting served and whatnot. If you click on this, well, you can see what time we're at here, 37 minutes, 39 minutes into the simulation. You click on this little gear here and speed it up. Here, let's run it at 10x. So you can see the coffee is kind of shooting through now. And the idea here would be to do a relatively lengthy run to get a good estimate of your parameters, but you'd also want to do multiple runs, and I'll just demonstrate how that looks before we end the clip. So happily, as we would expect, the valve utilization is 0 because there are no valves. The utilization varies through the day. There's some variation here because of the variation in both the service times and the inter-arrival times. But you can see roughly it's estimating right now that we're at about 56% utilization. Running a clover here, it estimates it to be at 52% currently. It's a little bit over. And so our numbers are building up. So some of the key performance indicators here, CX, of course, would be the waiting time, right? It's a big one. And then from the employee perspective, their utilization. So this clovers are currently 49%. That's the estimate, at least, utilized. So I'll run this to completion. And now it's running. Okay, should I click on that? So you can see it's really accelerating now through tens of thousands of minutes, up to 19,000 minutes. And that estimates it to be 48%. And if I scroll down here, there's 49% here as well. Okay, there's a 3D animation as well if you want to look at that. So I want to run this one more time. You will have to do multiple runs to get reasonable estimates. It's not going to vary that much, but just makes solid sense. So now you see it's run all the way again. Now I've got 47% on the utilizations. You can see the distribution's tight around that number. and the waiting time is 1.47, so your time in the system is 1.47 seconds from time of arrival to time of receipt of caffeinated beverage. So we'll do one more time, just to emphasize that, these simulation runs do need to be executed multiple times. This time I got 48, 49 down here. There's a small difference between the utilization captured here. This one is apparently based on, we have to look up the technical details here, but I think on the last 317 customers running through there, which is enough. This one, I think, would be based on pretty much the whole data set. So you can see global utilization base is based on 18,997. So maybe more reliable here. But they're very close. Okay, so you've got some variation. You've got an ability to, change these parameters and analyze the different scenarios. Enjoy.